Hi everyone! In this video, I'm going to introduce you to smart materials, one of the most fascinating topics in modern engineering. So, what exactly are smart materials? They're stimuli-responsive materials, meaning their properties change in a controlled and reversible way when exposed to things like stress, temperature, electric or magnetic fields, light, or moisture. In simple words, smart materials can sense changes in their environment and respond accordingly. That's why they often act as sensors, actuators, or even both. Think of it like this. A smart material connects an input to an output. For example, in a piezoelectric material, when you apply a mechanical force, it generates an electric charge. That's the output. As shown in the block diagram, when an external stimulus is applied, you get a measurable response. And that's what makes these materials truly smart. Let's look at this diagram showing various effects in materials. It represents how a materials connect an input, like electric field, stress, or heat, to an output such as charge, magnetization, or strain. This coupling between input and output forms the basis of smart materials. Every material interacts with its environment. It takes some input stimulus and produces a measurable output. When an electric field is applied, materials may show several effects. Permittivity and conductivity determine how they store and conduct charge. The electromagnetic effect couples electric and magnetic responses. The converse piezoelectric effect produces strain when an electric field is applied. This is the actuator mode of piezoelectric materials. The electrocaloric effects involve temperature change due to electric fields. Electro-optic effects change optical properties when electric fields are applied. The magnetoelectric effect couples magnetic and electric responses. Permeability describes how a material allows magnetic flux to pass through. In magnetostriction, magnetic materials change shape under a magnetic field. Magnetocaloric and magneto-optic effects behave similar to their electric counterparts such as electrocaloric and electro-optic part where input is magnetic field. Thus in this way we can relate all input and output properties of materials such as piezoelectric effect, piezomagnetic, and so on. In this chart, the diagonal couplings represent ordinary material properties like permittivity, conductivity, permeability, elastic constant, specific heat, and refractive index. These properties are well known and materials having these are called trivial materials. The off-diagonal coupling, except the diagonal ones, indicates some exceptional phenomena and is known as smart material behavior where two different physical domains are linked, such as stress to charge or heat to electric field giving rise to piezo and pyroelectric effect. Thus smart materials can sense and respond, functioning as sensors, actuators, or both, depending on how they are designed. Now in this table, the first column dictates the sensors and fourth highlighted column denotes the actuator. Thus a sensor detects changes in physical quantities, like temperature, pressure, or motion, and converts them into signals, while an actuator receives control signals and converts them into physical actions such as movement or force. Now notice the shaded regions in brown color. These represent smart material effects, where two different physical domains are linked, like stress to charge or heat to electric charge. This cross-coupling allows the material to act as a sensor, actuator, or both. So, in short, smart materials are unique because they can sense a change and respond intelligently, making them essential in modern engineering and smart systems. Thus, this table gives a detailed description of all these interrelated properties which you can have a look upon by pausing the video. Detailed discussion about these other properties will be discussed in later video. Thank you for staying up to the end of the video.